Have you ever wondered what makes milk opaque or why fog appears the way it does? These everyday phenomena are more fascinating than they seem. The answer lies in colloidal dispersions, often called colloids. These are mixtures where one substance is dispersed evenly throughout another. Colloids are everywhere in our daily lives, from the food we eat like salad dressings and mayonnaise, to the medicines we take, which often rely on colloidal formulations for effective delivery, and even the air we breathe, filled with tiny particles that affect our health and environment. Imagine a mixture where tiny particles, too small to be seen with the naked eye, are dispersed evenly throughout another substance. This is the essence of a colloid. These particles, ranging in size from 1 nanometer to 1 micrometer, are larger than molecules in a true solution, but smaller than the visible particles in a suspension. This intermediate size gives colloids their unique characteristics. This unique size range gives colloids their remarkable properties such as the Tyndall effect, where light is scattered by the dispersed particles, making the mixture appear cloudy or opaque. This scattering of light is what makes colloids so visually interesting. Colloids are like the chameleons of the chemistry world, existing in various forms. They can adapt and change, appearing in different states and combinations, depending on the combination of the dispersed phase and the dispersion medium. This versatility makes colloids fascinating and useful in many applications. When a gas is dispersed in a liquid, we get a foam, like whipped cream or shaving cream. These foams are light and airy, making them perfect for culinary and cosmetic uses. When a liquid is dispersed in another liquid, it's called an emulsion, like milk or mayonnaise. Emulsions are crucial in food science and medicine. Lyophilic colloids, meaning solvent-loving, are formed when the dispersed particles have a strong affinity for the dispersion medium, like gelatin in water. These colloids are stable and easy to form. Lyophobic colloids, meaning solvent-hating, are formed when the dispersed particles have little to no attraction for the dispersion medium, like gold nanoparticles in water. These colloids require special methods to stabilize. Understanding the classification of colloids helps predict their behavior and properties. This knowledge allows scientists to manipulate colloids for specific purposes. This knowledge is essential in various fields, from designing new materials to developing effective drug delivery systems. The study of colloids opens up a world of possibilities in science and technology. Colloidal dispersions possess unique characteristics that set them apart from true solutions and suspensions. Colloids consist of two distinct phases, the dispersed phase and the dispersion medium. The particle size in a colloid typically ranges from 1 nanometer to 1 micrometer, leading to a large surface area to volume ratio. This large surface area plays a significant role in the properties of colloids, such as their ability to absorb substances onto their surfaces. Brownian motion, the random movement of colloidal particles, helps keep the particles suspended and prevents them from settling out due to gravity. These characteristics give colloids their unique properties, including their optical, kinetic, electrical, and stability properties. One of the most fascinating aspects of colloidal dispersions lies in their optical properties, particularly their ability to interact with light. This interaction is not just a simple reflection or refraction, but involves complex scattering mechanisms that can be observed in everyday materials. Colloids exhibit the Tyndall effect, where light is scattered by the dispersed particles, giving the colloid a cloudy or opaque appearance. This effect is easily noticeable when a beam of light passes through a colloidal solution, making the path of the light visible. The intensity of the scattered light depends on the size and concentration of the particles and the wavelength of the incident light. Larger particles and higher concentrations result in more intense scattering, while different wavelengths of light can produce various visual effects. Some colloids can also absorb specific wavelengths of light, leading to the appearance of color. This selective absorption is what gives many colloidal solutions their distinctive hues. This phenomenon, known as selective absorption, is responsible for the vibrant colors observed in many gemstones. The unique optical properties of colloids make them fascinating subjects of study in both natural and synthetic materials. The optical properties of colloids have significant practical applications, such as in instruments like nephelometers and turbidimeters. These devices measure the turbidity or cloudiness of a solution, which is crucial in various scientific and industrial processes. Understanding these properties is crucial in industries like paint manufacturing, food processing, and pharmaceutical development. The ability to manipulate and measure light scattering and absorption in colloids can lead to innovations and improvements in product quality and efficiency. Colloidal dispersions are dynamic systems where particles are in constant motion and often carry an electrical charge. Brownian motion, the random movement of colloidal particles, helps keep the particles suspended. Colloidal particles often carry an electrical charge, which creates electrostatic repulsion between the particles, preventing aggregation. The electrical properties of colloids can be manipulated by changing the pH or ionic strength of the dispersion medium. The point at which a colloid has no net charge is called its isoelectric point, where the colloid is least stable. Understanding these properties is essential in various applications, such as in the pharmaceutical industry for ensuring drug stability. In water treatment plants, manipulating the electrical properties of colloidal contaminants helps remove them from drinking water. One of the key challenges in dealing with colloidal dispersions is maintaining their stability. Colloidal stability is influenced by a complex interplay of forces, including attractive van der Waals forces and repulsive electrostatic forces. Stabilizing agents, such as surfactants or polymers, adsorb onto the surface of the colloidal particles, providing either electrostatic or steric stabilization. Electrostatic stabilization occurs when the stabilizing agent imparts a charge to the particles, increasing their repulsion. Steric stabilization involves the creation of a physical barrier around the particles, preventing aggregation. Maintaining colloidal stability is crucial in various applications, such as in the food industry to prevent separation and in pharmaceuticals to ensure bioavailability. Understanding these factors helps in creating stable colloidal systems for various uses. Colloidal dispersions play a ubiquitous role in our everyday lives, impacting everything from the food we eat to the medicines we take. In food, colloids are everywhere, such as milk, an emulsion of fat globules in water, and mayonnaise, combining oil and water held together by egg yolk. Ice cream relies on colloidal science for its smooth, creamy texture. In pharmaceuticals, many medications are formulated as colloidal dispersions to improve their solubility, stability,